So good morning, everyone. I'm going to talk about privacy-preserving key derivation from biometrics, and specifically from face images, and how we help in closing the gap between theoretical and practical results. This is a joint work with Rita and Or, as Or just mentioned. And the idea is very easy. We have Bob, and we want to help him in generating a cryptographically strong key. And he wants to be able to generate the same key every time. And we're going to generate it by him standing in front of a camera. We're going to take his picture, and we're going to use his face image to generate that key. At the same time, we want to preserve the privacy of Bob, meaning that we can't store his image on the database, because if anyone sees it, he can learn that Bob is registered into the system, and he can steal his private information. So key derivation in general is generating a cryptographically strong key from information that the user possesses. It can be his biometrics, his fingerprint, his face image, etc. Or it can be a password that he knows, which is the widely used mean for deriving cryptographic keys. However, passwords have many weaknesses. So as we know, people forget them. And there are all these kinds of mechanisms that are used for recovering keys. However, those mechanisms are vulnerable themselves. And actually, once Bob remembers his password, a shoulder surfer can be standing just behind him, and he can observe the key, or the password, sorry. At the same time, passwords have very low entropy, meaning that we can guess them. And finally, they are carried over between systems, meaning that many people use the same password on Facebook and Gmail and all the services, many other services that they are registered to. So seemingly, biometrics can help us solve the problems. They have high entropy. Some of them can be easily observable, like faces, but they can't be easily copied. And it's very hard to forget them, right? It's very hard to forget your fingerprint or your face.
What are the estimates about the entropy content of biometric data?
We're able to show an entropy of about 511 with the representation that we get, as I'm going to show later. So the problems with biometrics, however, is that they are almost impossible to replace once revealed, right? So we have only one face, and if you use it to generate passwords, once it's stolen, we can't replace it. And we have only 10 fingers, so we can replace our fingerprint 9 times, and then we're stuck. And the privacy of the users is very important to us, and we don't want to compromise it. So I'm going to give you some background on how previous work tried to solve these problems. And afterwards, I'm going to present our system, Secure Face, for generating about 184 bits from face images. So another problem with biometrics is called the Fuzziness Problem, meaning that two samples of the same biometric source are almost never the same. So if we take a face image, and for example, those two face images, they look to us almost the same, right? At the same time, if we compare the pixels in those images, the majority of the pixels, more than 86,000 pixels, are different, whereas only about 3,000 pixels are the same in those two images. And those changes can be because of changes in lighting conditions, in pose, in expression, and many other variations in the environment. At the same time, we want to generate the same key every time that that we sample the biometrics. So merely taking the hash of the biometric source is not a solution. And usually in previous work, the fuzziness was handled either by using feature extractions, which is robust to all these kind of changes, and the use of error correction codes as part of the cryptographic constructions. which I'm going to show later. So the process for handling noise usually involves feature extraction, in which we go from pixels into some other features. And this feature extraction is usually robust against small changes in, say, lighting and all kinds of small distortions. And once this is done, we do some kind of binarization because it decreases the noise. It gives us more stable representation, although it does not eliminate the noise entirely. And it's also necessary for using all these kind of all the cryptographic constructions that I'm going to show later, and using error correction codes that store helper data to help us correct all the remaining errors after binarization. So for feature extractions, there are two general ways to do them. One way is more or less user-specific. And for example, the case in eigenfaces as well as Fisher faces. We collect the images of the users of the system, and then we do some kind of training and store user-specific parameters, which, for example, can be a set of vectors or images that span the subspace of phased images of the users. The other type of feature extraction is more or less generic, meaning that we compute some kinds of histogram and we convolve the image with some kind of filters like the Gabor features. And those kinds of features do not require any kind of training on the users of the system. Now, the problem with user-specific features, although they are accurate, is that we'll need to store private information, which could compromise the privacy of the users. So for example, in feature faces, if we look at the feature face once we stack look at the vector as an image, it looks very similar to a potential user of the system. And therefore, we should be very careful when we use these kinds of features. And if we want to actually maintain privacy, perhaps it's not a good idea to use these kind of features. As for binarization, as I said before, it's essential for using the cryptographic constructions like secure sketch and fuzzy extractors. Some previous work claimed that it's used because of its non-invertibility. However, one can try to approximate how the image actually looks. And yeah, one should be very careful with these kinds of claims. The way that binarization works is by taking the sign of the projection. So one way to do it is simply compute the features and then have all these kind of hyperplanes that we project the feature vectors on. And we take the signs of those projections and we have a binary representation. The other way that's more accurate, excuse me, is by doing some kind of quantization. However, for quantization, in many cases, we'll have to store some kind of private information to have a very accurate quantization or representation after the quantization. And well, since privacy is our goal, we're not going to use quantization, but rather we're going to focus on the sign of projection, on projecting the feature vectors on hyperplanes and looking at the sign. So how do the cryptographic constructions look like? One known construction is the secure sketch construction by Jules and Wattenberg. And the idea is very simple. We take the binary representation that we have and say that we want to enroll a user. We first select the key randomly, and we try to bind it to the user. So we select the key and encode it. And we take the binary representation, we XOR them, and we get helper data. This helper data is going to be used in the future to correct the errors that remain after the binarization. I'm going to show an illustration of this later, just in a slide. At the time of key generation, the user will provide us with another binary representation of his, like his biometric template. We're going to compute it. And we're going to XOR it with S. Now, if this biometric template is very close to the one that was used at the time of enrollment, then by XORing with S, we're going to be in the very close proximity of the encoding of the key. Then if we do the decoding, we're going to get the key. Other constructions include fuzzy vault, which works in the edit distance metric instead of the Hamming metric, as well as fuzzy extractors, which try to handle non-uniform representations, which I'm going to talk about, which is actually a requirement for those biometric template. Otherwise, we're not going to have any security or privacy guarantees. So here's an illustration of how Secure Sketch works. At the time of enrollment, we compute a biometric template that we want to enroll, we want to use for enrollment, and we select a key randomly and encode it. Now, say that this error correction code corrects up to T errors. This means that in the future, if we sample, we find the biometric template that is close up to T to X enroll, we can use S, the helper data, to do the translation to the close proximity of the encoding of the key. And after decoding, we're going to get the key. However, if someone tries to deceive us and create a key that belongs to some other user, his biometric template is going to be too far. And after translation by S, we're going to still be too far from the sphere around the encoding of the key. Does this make sense? When it comes to practice, Jules and Wattenberg showed that the biometric template must follow uniform distribution in order for us to have no privacy loss, in order to have a key that is, has very high entropy. However, when it came to practice, people actually created biometric templates that did not follow by uniform distribution. So for example, Howard showed the process of creating 140 bits of entropy from iris images. However, statistical attacks, since this biometric templates that they found did not follow uniform distributions, one could apply some kinds of statistical attack and exploit dependencies between the bits, as well as the helper data, in order to guess the key in 2 to the 10 guesses, which is a very huge difference. While fuzzy extractors can help us generate a uniform distributed, can help us handle this non-uniformity in the biometric template, usually the entropy loss is too high, and we can end up even with negative entropy, God forbid. So it's not very practical to use fuzzy extractors. To sum up, the challenges that we have is that the data that we use for feature extraction, like in the case of feature faces, can reveal personal information about the users of the system. We need a uniform distributed biometric template in order to use Secure Sketch. And if we want to correct for that and use fuzzy extractors, usually the min entropy loss is too high, and we remain with very short keys. So in our system, we try to tackle those challenges. And as I'm going to show, we create about keys of length 184 bits of entropy. So the way that our system works is, first of all, we do feature extraction, and then we do the binarization. And once we will set on that, we can choose the error correction codes that we're going to use as part of Secure Sketch. For feature extraction, the first step is simply doing some kind of transforming the face into some normal pose. And the reason for that is that we don't have the enrolled image at the time of generating the key, right? So we can't actually take the image at the time of generation and align it with the image at the time of enrollment. To this end, we find 5 landmarks on the face and do transformation into some normalized pose. Once that is done, we can compute generic features, because they are non-user specific, from different regions of the face. And we use standard features that are used in computer vision, such as local binary patterns, as well as scale invariant feature transforms, or SIFTs, as well as, and finally, we compute the histogram of oriented gradients from the whole image. So once we compute all those features, we can reduce the dimension of each feature vector and stack them together. This gives us a distribution that's more or less Gaussian. However, this Gaussian is not symmetric. Now, to create independent bits, one way to do this is to have a symmetric Gaussian and then try to project the features on orthogonal hyperplanes. To do that, to get this symmetric Gaussian, what we can do is we can remove the correlations of the features that we got here by projecting on the principal components. And once done, we can rescale each feature that we get into the 0-1 interval. Once this is done and we have a symmetric Gaussian distribution, what we can simply do is doing the projection on orthogonal hyperplanes and taking the sign, and we'll get independent bits.
So this, if I understand correctly, this removes the linear correlations between the features, but do you have an indication that, like, what are other indications?
Oh, we do some statistical tests to convince ourselves that this actually works, as I'm going to show in the end. So once we have the features and we have this beautifully distributed features, we can create the binary representation. Now we only need to find the hyperplanes. And we want hyperplanes that, after projection, will give us consistency and discrimination between the binary representations. We don't want to have correlation between the bits, meaning that we want to have orthogonal hyperplanes, and want to have high entropy. Now, the same requirements, interestingly, were asked in a paper from 2010 for solving the approximate nearest neighbor problem. The idea is that we have the features of the users of the system, or as we're going to show, we're going to use different users or different subjects. And those features either belong to the same person, or the pairs belong to different people. And what we want to do is to find hyperplanes, W1 till WK, and we want the projection on these hyperplanes to give us equal bits for a representation that belong to the same person, and unequal bits otherwise if the features belong to different people. However, if we find W by doing the training on the users of the system, we're going to have information that tells us about the users of the system, which is actually undesired if you want to maintain privacy. One solution to solve this is by doing transfer learning. The idea is that we do the training on subjects that are not going to be enrolled in the system. And instead of learning a representation that are consistent to each one of the users, we will kind of learn K hyperplanes, or okay, I changed the notation a little bit here, such that each hyperplane tells us more or less about an attribute that either person has or doesn't have. So for example, the first hyperplane could be telling us whether the person is blonde or not, or whether he resembles some other person or not. So once we have this matrix of projection hyperplanes, we more or less have the whole system, right? We take an image, we do the feature extraction and binarization, and then we use secure sketch. We encode the key, we XOR with a binary template, and we get the helper data at the time of enrollment. At the time of key derivation, we'll do the same. The user will provide us with his face image as well as the helper data. We'll do feature extraction, binarization. If it's the same user, or the biometric template is close enough, S is going to translate us to the proximity, the close proximity of the encoding of the key. We can do the decoding, and we get K. Only two minor things are left to figure out. What's the decoding and the encoding function? What's the error correction code, in other words? Before we do that, we can look at the results of the experiments and see how the distances between different people and the people in themselves look like. To this end, we first did the training to create the matrix of projection hyperplanes, and for that we used subjects that are different than those that are enrolled in the system, and use this transfer learning thing. So we have more than 900 subjects, about 3 to 4 images per subject, and with that we're able to learn 511 hyperplanes that are more or less orthogonal. For evaluation, we used a database of frontal face images that was collected under controlled condition here at the University of Haifa. The idea is that if the changes in lighting and in the environment are too large, the biometric templates of the same person will be too far from each other. So we resigned it to taking images that are shot under controlled conditions. In this database, we have about 474 subjects, and 26 of them actually have more than one session. Here are, for example, images from the database, and we have about 6 images per person. So in the tests, what we compute is simply a simulation of genuine key derivation attempts and impersonation attempts. So we're going to take biometric templates of the same people or compare them and see what's the distance between them, and the biometric templates of different people and look at the distance between them and see how they are distributed. And the distribution looks something like this. So we see that for different people, the average distance is about 255, which is actually half of the representation length. And that the minimum distance between two different people is at least 164. Whereas we see that the distances between people and themselves are much less. And if we take this point at 164 as the threshold, then we're never gonna so if we have an error correction code that can correct only up to 163 errors, then an imposter will never succeed into generating the key of some other person. And if you look at the ROC curve, this gives us about 89% true positive rate and 0% false positive rate, meaning that, again, we're never deceived by an imposter. So again, what's left is simply figuring out what error correction code we use. As a first attempt, let's try to find an error correction code above the binary alphabet, the 0-1 alphabet of length 511. So we want to correct 163 errors. Based on that, the diameter of each sphere in the space is 327. Now, what the Plotkin bound tells us is that the number of code words in this error correction code is less than 4.57. Now, based on that, we learn that we can generate keys with less than 3 bits. That's not what we want. As a second attempt, we can try to look at the literature for the best error correction code that we can find. And one option is Reed-Solomon concatenated with repetition codes, which has been shown in the work of Mace and Mace et al. And the idea is simply to encode the key. And once we encoded it, we can repeat it as much as we can until we get up to the length of the biometric template. So in our case, say that we want 80 bits of key. key of length 80 bits. The best parameters would be is to use Reed-Solomon with 16 symbols. Each symbol is 5 bits long. And in this case, the length of the code word is 31. And this Reed-Solomon error correction code can correct up to 8 symbol errors. Once we have it, we can do up to 3 repetitions. So we simply take each symbol after encoding and repeat it 3 times. The result is, here we have 31 symbols. Each is of length 5 bits. So this is 155. We repeated it 3 times. We have 465 bits. So we can take a subset of the bits we have in the biometric template and throw all the others, right? Of course, for decoding, it will work the same way. We can compute, of course, the helper data. Once we have a biometric template, we'll XOR it with the helper data, and we'll get this, right? For each bit, we're going to recover it by taking the majority. And once we have the code word or something in the space of the code word here in the Reed-Solomon error correction code, we can do the decoding and try to recover the key. So the question is, can this actually work for the numbers that we have? So we have, we said before that we want to correct up to 163 errors. Now these errors are unstructured, meaning that they can appear anywhere in the representation, and they are uncorrelated. Meaning that for each bit, we'll have about 32% chance that it's going to be erroneous, or a probability of 68% that each bit is correct. Now, after taking majority, right, with the repetition code, we want the bit to be correct. Meaning that we want, before majority, that at least 2 bits are correct or 3 bits are correct, right? The probability of that happening is simply this simple combinatorics, and this gives us that we have 76% that a bit is correct. Now this is only 1 bit in a Reed-Solomon symbol, right? So this tells us that, say, this is the probability that this bit in this symbol is correct. Now for the whole symbol to be correct, we want all 5 bits to be correct, right? So if you have 76% chance that the bit is correct, for all the 5 bits to be correct, we have only 25% chance. And if the error correction code has 31 symbols, then approximately 23 symbols will be wrong. But as I've shown just before, for this error correction code, we can correct only up to 8 symbols, mistakes in symbols. And this construction can't really help us. Just as a last word for this, on this, the problem here was simply that a correct bit in the biometric template did not ensure that a symbol in the error correction, in the Reed-Solomon error correction code was correct, right? A wrong bit ensured that a symbol is incorrect. However, a correct bit did not ensure that the symbol is correct. And we want to try to solve this. We want to make sure that a correct bit in the biometric template gives us a correct symbol. The idea in our construction is to do the repetition on the biometric template instead of doing it on the key. So we select a Reed-Solomon key with L symbols. Each symbol is of length m bits. This gives us 2 to the m-1 symbols length code words. So we have L symbols, and each symbol has m bits. We encode them, and we get 2 to the m-1 code word, symbols length code word. What we do is we take a biometrics of length 2 to the m-1, and we repeat each bit m times. After doing that, we get an extended representation of the same length as the code word. Now, if you look at this, suppose at the time of deriving the key, we have a correct bit for x1 as in the time of enrollment. Then we'll be able to generate the whole symbol correctly, which was not the case for the previous construction. So we still compute the helper data in the same way. And as I just said, correct bit in this case ensures a correct symbol. Now the question is, what are the parameters that we can use for our system? In our system, the length of the representation is 511. This means that M is 9. We used symbols that each has 9 bits, and we extend each bit in the biometric template n times. And in order to correct up to 163 errors, we can select a key of length 184. The question is, what are the privacy and security guarantees that we get? What we show is that if X is uniform distributed, then the entropy of X of the biometric template given the helper data is L, which is technically the number of symbols that we have in the key. To give you a flavor of how we show that, suppose that we have X and we're able to guess the first L bits of this biometric template. If we do that, we can XOR those L bits with the helper data. And and we recover in this way L symbols of the key. Now, if we have L symbols of the key, we have the whole key. And once we have the key, we XOR it with the helper data, and we get the biometric template. So that's why we have at most L bits of entropy. However, our biometric template might be not totally or exactly uniform distributed, but almost uniform distributed. So if we have a little loss in the entropy or a small difference than uniform distribution, we lose only up to R and the privacy. The same thing goes for security. If X is uniform distributed, we're able to show that the entropy of the key given the helper data is L. And if it's if it's only up to R from having full entropy, then we'll almost get full security in the key. What remains is for me to convince you that the biometric template that we find is uniform distributed. One way to do that is by showing that there are no correlation between the bits and that we have high min entropy for each one of the bits. One way for doing that is using degrees of freedom. Now, if the biometric template was of length 511 and all the bits were independent of each other and each had probability half of being 0 or 1, then we would get degrees of freedom that are equal to 511. In our case, we get 509 degrees of freedom, which tells us that more or less we have independence between the different bits of the biometric template. We can also try to look at the covariance matrix of the biometric template. And we see that it's diagonal, and all the off-diagonal elements are almost 0. So this shows that they are uncorrelated. And finally, if we look at the min entropy of the representation, since they are more or less uncorrelated, we can look at the min entropy of each and each bit. If we sum them up, we get very close to 511. So once I showed that, I hope to have convinced you that we have more or less 184 bits key with entropy 184 given the helper data. So to sum up, I've presented to you a system for generating strong cryptographic key from face images. It provides consistency and discriminability, meaning that we have about 89% true positive rate, meaning, which means that a user will succeed in deriving his key in 89% of the times, whereas an imposter will never succeed in doing so. We have provable privacy and security, and it can be used as an alternative for key derivation. And that's all. Feel free to ask questions.